Hey guys, good morning.
Morning.
The key is posted upstairs, third floor. The test will be returned on Friday. Chlorine lab. I sent out an email. Everybody got the email? The reduction of the nitro to the amino. I don't know. When I do it, I get like 60–70% yield, but it seems like our average yield for you guys is 30–40. It's not enough. I'd like to make the procedure bigger, larger scale or something, but in the end, I'm not satisfied with the procedure. I'm going to give you some amine. Okay? You'll get that today. Not an open bottle, but you'll be handed some. Okay? There will be a sign-in sheet or a sheet that you keep track of who gets amine. If you don't get amine, that means you did a good job with the synthesis and you didn't need it. Okay, you did the diazonium to make the iodo. The iodo you then use to make the Suzuki reaction, which is to replace the iodine with another phenyl or a benzene ring. That's a Nobel Prize winning reaction using a boronic acid. If you don't have enough iodo, I send a procedure for making that. You can make this directly from fluorine by iodinating it. You'll see that procedure was an attachment. From the amine, you have two reactions to run. You have to make one amide, either the benzamide. Okay, we're starting acid derivatives today. An amide is an acid derivative with the benzene. It's called a benzamide, or some people say benzamide, or the acetamide. That looks like acetic acid. Acetamide comes from acetic anhydride. Here we use an acid chloride. We'll talk about both ways to make amides. Your choice. Only one is required. You also have to make the imine. Imine is a carbon-nitrogen double bond, analogous to a carbon-oxygen. It's analogous to a carbonyl. It's an imine. Everybody has to make the imine. From the imine, you will reduce the imine to the amine, or the amine, using sodium borhydride, which we've talked about several times. Everybody has to do this. You have to do one fluorine. You either have to have fluorine on this guy or on this guy. If you make the acetamide, then you have to have fluorine here. You can make the benzamide without fluorine, just H. Then you'd have to have fluorine here. If you have fluorine here, then over here it can be not fluorine, but chlorine or bromine. You can only make one fluorinated compound. All those instructions are clear. Any questions about the fluorine lab? Also, some of you have the oxidation going, where you oxidize the benzylic carbon. This can be done with just oxygen in the air. It's just an air oxidation, O2. Because that's doubly benzylic, it's sort of doubly reactive for oxidation. And with base, it'll air oxidize. That's a nice product. Usually recrystallizes very nicely. Some of you have that in your drawer right now. Okay. So acid derivatives, where we're starting today. Test 3 is carboxylic acid derivatives. From here on out, it's carbonyl chemistry. Test 3 and 4. Test 3, acid derivatives. Test 4 will be aldehyde ketone derivatives. Now thrown in there is a little bit of non-carbonyl chemistry, but everything will be associated with carbonyls in some way. Okay, we need to, you certainly need to know your functional groups. And the first page illustrates this. Everybody have a handout. Start going around in the back. Did you take all of these?
Yeah. Well, the allergy ones.
Okay. So, here's your carboxylic acid. Okay? Carboxylic acid is sort of the king of the functional groups. There's two antihistamines. We have esters. So this anticoagulant, blood thinner, an ester group. This would be a methyl ester. So you replace the H with an R group, methyl ester, ethyl ester, propyl ester, whatever. Analogous to a regular ester is something you didn't see in organic 1, but a thioester. That's where instead of a OR, it's an SR. Now that's an R group, it's a carbon, it can have anything on it. But right there's your thioester. I point those out, well, because there's a drug that everybody knows, Flonase. Okay, thioester. You'll also see thioesters in biochemistry. And when you get to biochemistry and you see thioester, everybody's going to say you've seen it before, right? Okay, amides. Carbonyl with nitrogen, one nitrogen, amide. The nitrogen can be substituted and it's still an amide. So with amides you have primary, secondary, or tertiary amides. This would be a tertiary amide because the nitrogen has three carbons attached to it. 1, 2, 3. Here's another amide. That's one. A secondary amide. Nitrogen has 2 carbon groups. You also have nitriles. Okay? And so verapamil, nitrile there. Nitrile does not have a carbonyl. How's that an acid derivative? Well, what's the definition of an acid derivative? It comes from a carboxylic acid, essentially. And it can revert back to a carboxylic acid. What's another definition? All these functional groups, the carbon of the functional group has how many bonds to a more electronegative atom? Right there. How many bonds to a more electronegative atom? 3. How many bonds to a more electronegative atom? 3. 2 to the carbonyl oxygen and 1 to the OH. How many bonds to a more electronegative atom? 3. 1, 2, 3. 3 to the end. An acid derivative, the carbon of the functional group, is going to have 3 bonds to a more electronegative atom. For example, acetone. That's a carbonyl. Is that an acid derivative? How many bonds to a more electronegative atom? 2. Only 2. It is not an acid derivative. Number of bonds to a more electronegative atom is actually oxidation state. This is not at the same oxidation state as an acid derivative. It needs to be oxidized to get to an acid derivative. Okay? All your acid derivatives have how many bonds to a more electronegative atom? 3. Okay. Let's look at the back. In the back, there's what's called an imide. That's probably not going to be in your textbook. An imide is a nitrogen that's bonded to 2 carbonyls. If that was not there, that's an amide. Amide. If the nitrogen is bonded to another carbonyl, actually this is not right. I was going to make a point, but my point is not right. Forget it. That is an acid derivative. I was thinking it was not. Never mind. I'd have to show you another one. Everybody know what urea is? What's urea? That's urea. Okay? Carbonyl with NH2 on both sides. Is that an acid derivative? No, why not? Because that carbon has 4 bonds to a more electronegative atom. Okay? Not an acid derivative. You would have to do redox to get to that or to this from an acid derivative. Okay. I was thinking an imide was not, but actually an imide is. You actually have two carbonyls. Okay. So there's that. We turn over, we'll look at nomenclature. Before we look at nomenclature, you can look at this molecule. Anybody know this molecule here? That's LSD. You know, it's only about 20 carbons and about 2 or 3 oxygen and nitrogen. Yeah? Okay. But it's arranged in a very nice way, and it elicits a response in the body. What does LSD stands for? If this was an OH, that'd be a carboxylic acid. That'd be lysergic acid. Okay? This is an amide of lysergic acid. It's actually the diethyl amide of lysergic acid. The D stands for diethyl amide. Okay? You can read about when the guy first discovered it. He took some and then rode his bike home. You can read about it. Okay, let's look at nomenclature. So, carboxylic acids. Longest continuous chain. 1, 2, 3, 4. Butane. We replace the E of butane with oic acid. So this becomes what? Butanoic acid. Replace the E with oic acid. The carbonyl of the carboxylic acid is your one position, always. And then you go out from there. Let's name this guy down here. Longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8.
No.
No, it's not stated here, but the carboxylic acid needs to be in your longest continuous chain. So you can't say 8 and that'd be outside. You might as well start right there as 1. From there, what's the longest continuous chain? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. 6 is longer than 5. Right? So what do we have here? Not hexane, but hexanoic acid. What's on the hexanoic acid? We got a propyl at what position? 2. 2 propyl hexanoic acid. Looks like it should be all one word. 2 propyl hexanoic. Acid is a separate word. Look pretty straightforward. Okay, some common acids over here. This is acetic acid, just a mouthful coming off. Okay, if you named it according to Aliphatic, what would this be? Ethanoic acid, 2 carbons. Yeah, but nobody calls it ethanoic acid. Go to the stockroom and ask for ethanoic acids, somebody's going to look at you weird. Okay? It goes by the name of acetic acid. Okay? The carbonyl, the 2 carbon with the functional group, that's like acetic. You can't have this carboxylic acid with just an H coming off. That is a stable acid. That's called formic acid. You might be trying to call it methanoic acid because it's 1 carbon. Nobody calls it methanoic acid. It's called formic acid. Where do you find formic acid? Cereal. Everything else is there, but I don't think formic acid. Ants. Ever been bitten by an ant? What do they inject you with? Formic acid. It stings a little bit. What's the scientific name of an ant? Something formica. Yeah. I don't know which came first, the scientific name of the ant or the name of the acid. But formic acid is a large constituent of ants. Actually, you can take like a whole bunch of ants and put them in a flask and heat it up, and formic acid will distill out. And you'll be left with dried ant carcasses in your flask. Okay? I don't know. I'm not that up on my ant. Okay, amino acids. Okay, alpha amino acid. That's where there's an amine on the alpha position. The first carbon coming off is called alpha. Okay, that's actually the 2 carbon. but in terms of more generic, that's the alpha, next is beta, next is gamma. Okay? Alpha amino acids have this structure when the R group varies here. This substituent varies. You'll see all those in biochem, all your essential and non-essential amino acids. Also here, GHB. What is this? Anybody heard of GHB? Date rape drug. Okay? Very simple molecule. It's got hypnotic properties. What does GHB stand for? Name this compound. What's the longest continuous chain? So what do we have? Butynoic acid. What's on the end position? What's the name of the substituent? Hydroxy. What position is this? You can call it 1, 2, 3, 4. You can also call it what? Alpha, beta, gamma. Gamma hydroxy butynoic acid. GHB. Make sense? Okay, let's look at nomenclature of esters. Esters have two fragments. It has the sort of the acid fragment, which is that's your acid fragment. But then you have the R group that's put on that to turn it into an ester. You have two names. You name the acid fragment, and then the R group. The R group goes in front though. Okay, this acid fragment here, you got to recognize, okay? If that was an H, there's your acid. So that's the acid fragment. 1, 2, 3, 4. And some call it butynoic acid. It's called butanoate. So what are we doing here? We're replacing the E of butane with O8. Hexanoate. Octanoate. The one position is your carbonyl going that way. Then you say, okay, what's the R group on the oxygen? That's an ethyl. So the name of this is ethyl butanoate. What would methyl butanoate be? That'd be where there's just a methyl on that butanoate. You can have butanoate and then a million different things on that portion. Could you draw hexyl butanoate? Yeah, it would be this. You just have a hexyl here instead. Let's see more of this by doing another example. Now the one position is here going this way, and the one position on this guy, if you have any substituents, the first carbon is your 1. Okay, let's try here. What's the acid fragment? 1, 2, 3, either way you go 4. So that's also a butanoate, yeah? What's on the butanoate? Methyl, at what position? 3-methyl butanoate. So that's what we have there. What is the R group that's on that acid fragment? Ethyl, 2 carbons. But what's on the ethyl? At what position? 2-fluoroethyl 3-methyl butanoate. 2 separate words. Does that look right? Is that a 2-fluoroethyl that's on the oxygen? And is this a 3-methyl butanoate? Hopefully that looks right. Do the one on the right. Okay, what's the acid fragment? 1, 2, 3. We got what? Propanoate. What's up? Somebody do something wrong? What'd you do wrong?
I didn't count the carbon. The other one. So I started counting.
1, 2, 3.
Right, I counted from just the carbons in the ring. So I only
Well, if
counted
that was an
two.
H, that would be propanoic acid. It's the same thing, except it's an ester, so it's propanoate. But what is the R group? Is there anything on the propanoate? No. Okay, what's the R group? I see the first carbon is 1, 2, 3. So that's also a propyl. So it's propyl propanoate. We have something on the propyl. What is it? 2-phenyl propyl. There's a phenyl. There's a benzene ring, but we call a benzene ring a phenyl when we're calling it a substituent. 2-phenyl propyl propanoate. Anybody have an issue with that name? Looks good, Mark?
It's pretty long.
Yeah, but it's hopefully pretty straightforward. Okay, amides. The long name of an amide is carboxamide. Because there's other types of amides. What type of amide is this? Sulfonamide. Okay? This is a carboxamide. Why carbox? Because it has a carbonyl. Now, carboxamides are often shortened to just amides. This is never shortened because it has to remain clarified. Now, this is real difficult. Here, you replace the E with amide. But if you say it, butanamide, well, usually it's said like butanamide. That's all we did, we replaced the E with amide. So butanamide, hexanamide, octanamide. That right there is butanamide. First carbon is 1 out. What is this? Now, with amides, you don't put the R group as a separate word in the front. And you usually don't, if we call this maybe 1, see if that was 1 methyl butanamide, you might think, well, is the methyl here? Very often it said N. The methyl was on the N. So it's a little bit different than esters. And it's all one word, N-methyl butanamide. How about the one at the bottom? Name that one. What is our sort of acid portion? This kind of came, if that was OHB acid, what do we got? 1, 2, 3, 4, 5, 6. Not hexane, but hexanamide. What's on the hexanamide? And phenylhexanamide. Some common ones on the side. We forgot to mention this. This is an ester of acetic acid, right? Acetic acid would just now have an ethyl on it. What's that called? Ethyl. What is that called? Not ethanoate. What do we call that? Acetate. Okay? But we don't call it ethanoate. We call it acetate. And that's the ethyl ester of that. What do we use ethyl acetate for? Very common solvent in the lab. Okay. What would this be? Sodium acetate. Of course, that's ionic. For your amides, you have, what if we had two substituents? You put two N's, NN dimethyl butanamide, 4 carbons. 2 N's. This is a common solvent. I don't think we've ever used it in lab, have we? DMF. NN dimethyl. If that was an acid, what would that acid be? That was OH. Formic acid. It's called formamide, because it's an amide. NN dimethyl formamide. Dimethyl formamide. DMF is a very common, very polar solvent. If you look on the back, no, over at LSD, it's the NN diethyl amide of lysergic acid. NN diethyl. And it might say that there. If you look it up on Wikipedia, it will probably say that. Did we name them all? Any questions about nomenclature?
Yes. What do you do if you have a substituent on your group that's attached to the end?
It would be numbered. For example, if we had a chlorine here, what would that be?
They're attached to the end.
Attached to the.
So the methyl, if it was a methyl, let's say, and it had a fluorine on it, attached to that.
Yeah, I'm really not getting into it. It's a good question. We probably did not cover it. You may recognize that. What we covered is sufficient. Yeah. I'd have to think about it. It may be as simple as just adding something in front of the methyl, but not needed. Okay. Before we get into the chemistry of amide derivatives, we're first going to look at, or acid derivatives. We're first going to look at acidity, and then some basicity. So a little review of acid-base chemistry. Carboxylic acids are your main acidic organic functional group. Okay? Do you know of any other functional group that's called acid? No. Carboxylic acid is your most acidic organic functional group. Unless you get into sulfonic acids, the functional group itself does not contain a carbon, but it may contain a carbon on the side chain, and then it becomes organic. Again, you can refer to the last page of your workbook that has a list of all your pKa's. Okay. These you pretty much need to know at this point. Alcohol is about 16. Phenol, about 10. So it's 1,000,000 times more acidic than regular alcohols. Why? The anion here is just localized. It has no resonance. All it has going for it is that the oxygen can handle a minus. Over here we have the oxygen. That's consistent across the board. But here we can start doing resonance structures, and we can delocalize the charge. Okay? You can do other resonance structures and delocalize it around the ring. Carboxylic acids are even more acidic, about 4 to 5. Why? Now here you can actually do 4 total resonance structures. So you can do 2 more. Here, you only have 2 total resonance structures. This being more acidic implies that this is more stable. It's more willing to give up the H and come here. Why? Why is this more stable when it doesn't have as much resonance structure? Valerie?
The charge is delocalized with 2 electronegative atoms instead of
Yes, yes. When we do resonance, we put the minus on another oxygen. But here, when we do resonance, we put the minus on what? Carbon. Carbon doesn't handle it as much, so these resonance structures do not contribute as much. So we have minus on 2 oxygens, delocalized over 2 oxygens. That makes it more stable, more willing to form carboxylic acid, more acidic. But putting it on putting it on carbon is better than putting it nowhere else. So there's some delocalization here. Because of this, we have consequences like solubility. Most alcohols are not soluble in aqueous base. Now, actually, ethanol is soluble in aqueous base, but not because it's becoming deprotonated, but only because it's soluble in water. If you get, let's put like a phenyl here. Now it's got lots of carbons. This phenyl is not conjugated, and so this is not a phenol. That's not soluble in water, and it's also not soluble in aqueous base by deprotonation. On the other hand, this is. This is soluble in aqueous hydroxide because how does this exist with aqueous hydroxide? With hydroxide, it's converted to the anion, and then the anion is ionic and it's soluble in the water that's also there. So you have to go back and remember your pKa's and your equilibrium. What's the pK of this? 10. When this reacts, you get that plus what? Water. What's the pK of water? 16. Which side's favorite, 10 or 16? 16 is favored because it's a weaker acid. By how much is that side favored? A million. 10 to the 6. If you put this in hydroxide, it's going to exist that way by a million to 1. All of your phenols become anions. At least 999 whatever out of a million do. Okay? Carboxylic acids, well, they're even more acidic, so they're even going to be even more in the anion. You treat these with hydroxide, these are converted to the anion, and so these are soluble in hydroxide. Carboxylic acids are also soluble in bicarbonate. Bicarbonate's a weaker base. It's strong enough to deprotonate a carboxylic acid, but it's typically not strong enough to deprotonate a phenol. We're not going to look at any pKa's with bicarbonate. Okay. What happens? Bicarbonate, it's in your kitchen as what? Baking soda? What happens when you put baking soda and vinegar together? Uh-huh. Why does that happen? This reacts with this to give what? O minus plus what? Plus the carbonate gets protonated. 10% solution in water, that's vinegar. This is what? What's the name of that guy? Carbonic acid. What happens to carbonic acid? It decomposes to CO2 plus water, and the CO2 bubbles out like a gas. Carbonic acid is not stable. Let's look at the effect of substituents on acidity. Phenols first. If you have a net electron donating group, that will make it less acidic. It will raise to pKa. If you have a net withdrawing group, that will make it more acidic. Well, does that make sense? If we're talking about a phenol being more acidic, we're back up here. What would make this more acidic? Stabilizing where it's going. This is becoming an anion. The anion is put into the ring. How do you stabilize an anion if you start having a substituent? Do you want a donating group or withdrawing? A withdrawing group will stabilize the anion more. As the minus is here, if we can withdraw, stabilize it. Withdrawing groups stabilize this, making this more willing to give up the H, making this more acidic. That's what we said right here. What if we have a donating group? Well, when this becomes minus and we donate electrons, that's not going to stabilize it. That would destabilize it. Donating groups make it less acidic or increase the pKa. Now, how do you know what a donating group is and a withdrawing group is? We learned it 3 weeks ago, right? It's the same as your EAS substituent effects. For example, there's phenol. It has a pKa of 10. It's written up there. What is it, 10.1 or 10.0? 9.8? 9.95. Okay. This has a pKa of 10.2. Less acidic or more acidic? Less acidic. Why? Because this is a net what? That's a net electron donating group, as we learned with EAS reactions. Same as EAS reactions. What type of group is nitro? Withdrawer. Group 4 withdrawer. Look what it does to the pKa. Makes it much more acidic. It's actually a strong withdrawer. What if we put 3 nitros on there? Here's a phenol that has a pKa of almost less than 1. Almost less than 0. 0.38. Now that phenol is more acidic than acetic acid. That phenol is actually called picric acid. It's actually an explosive acid, because if that was a methyl, what would that be? TNT. Okay? Lots of nitro groups tend to be explosive. Now let's look at this. Position matters. Paranitro 7.14, meta 8.28. Which is more acidic? Para. Why is this not as acidic? Has to do with resonance. Has to do with resonance. This is a lot like NAS. Where did the nitro or the electron withdrawing group have to be to do the NAS reaction? Ortho or para. Para. But more of an effect here. Why? Let's look back up here. I didn't show all the resonance structures, but if let's go ahead and show them all. Move these here, move these out. That's going to give that. Then we can move these here and move these out. There are your 2 additional resonance structures. Where does the minus fall compared to where the OH is, or the O? Ortho, para, ortho. If you want a group to do resonance and really have an effect, where do you want that group to be? You want the group to be there. For example, if I was to put on a ketone here, can we draw an additional resonance structure now? Right here, we'd be able to draw into the functional group and we'd be able to get the benefit of the resonance into the new functional group. If the functional group was meta, we would not be able to do that, because the lone pair never falls meta. And so you can do the same type of resonance structures, and you should sit down and do it for these here. Here, the anion, you can show resonance into the nitro. But here you cannot. You should sit down and do that. No resonance into the nitro. So why is it lower than phenol? Obviously it's more acidic. Because even though you can't do resonance, still you have inductive withdrawing of the nitro. And so you have only induction. Where over here you have induction and resonance, making it more acidic. That's going to take you sitting down and really looking at the resonance structures, okay? We just don't have time to sit down and go through all that. Let's look at this down here. Let's move to carboxylic acids. It's very similar to up there in terms of donating withdrawing. If this was an H, about 4.2. This is a bromine, more acidic. Why is it more acidic with a bromine? First off, we're really considering this here. Now, when you do resonance here, you cannot do resonance into the ring. You can only just do resonance onto the other oxygen. But still, if we have a net withdrawing group, we can still say it pulls and it stabilizes the minus. And what if this is a methoxy? What does it do? It's a net donator. So a net donator pushing minus towards this minus is not going to help that minus. It will make it less willing to form, and so it's not as acidic, higher pKa. But look at this over here. Not every methoxy is the same. If we put the methoxy in the meta position, it's actually more acidic than if it was not there. You recognize that? If we put a methoxy meta, it's more acidic than this. If we put it para, it's less acidic than that. I want you to think about why that is. So this means you can't just say, hey, this is a donating group that should lower the acidity. Why does it increase the acidity here? Think about it. Okay, let's look at acidity of aliphatic acids. Acetic acid 4.76. Chloroacetic acid more acidic. Why? Inductive withdrawal. Again, we're looking at trying to stabilize the minus. How does that chlorine stabilize the minus? Inductive pulling. What about 2 chlorines? Even more pulling, even more stabilization of the anion. What about 3? So there's 3 there. You get the idea? The more pulling you can provide to stabilize the resulting anion, the more willing it is to form. So does that make sense? Let's compare this to this. What if the chlorine is way out here? Not as acidic. Why? Because the pulling effect sort of tails off as it gets away from where the anion is going to be. But it's still more acidic than if up here. Because you still have some pulling, it's just not as predominant when it's closer. What if we switch to an iodine? Let's compare it to this one. Is this going to be more acidic or less than this one? Now we have a different halogen. What's the difference in iodine and chlorine? Iodine is less electronegative. So it's not going to pull as much. You think this should be more acidic or less than this? So that should be less acidic than that. I don't have an actual pKa, but I guarantee you it's less acidic. That iodine doesn't pull as much. We can sort of say something like this. If we have an electron withdrawing group, it's going to make it more acidic. If we have a donating group, it'll make it less acidic. Okay, we're moving away from acids. Any questions about any of the acid stuff? Hopefully most of it's fairly intuitive. You just kind of see it. You need a refresher. You see a few new things. It should be fairly straightforward. Which one? Oh, good. I was actually just thinking about that one. I'm going to draw it on the board. More acidic or less acidic than? Let's compare it to just here. If it was not there. More or less acidic? Didn't see a guess. Precious? Less acidic, why? How is this donating? How is this donating? It's a donating group in EAS. How does it donate in EAS? Starts with an R. Donates by resonance. How is this donating by resonance? There's no p orbital here. There's no resonance here. The only thing it does is induction. And with induction, how does oxygen do compared to carbon? That is just an electron withdrawing group here. You cannot just say all methoxys are donators. Donates by resonance. There's no resonance here. Show me a resonance structure involving that lone pair. We can't do it.
Is it more acidic with that than chlorine?
No, chlorine's more acidic because chlorine's a stronger electron withdrawer.
Okay.
Oxygen's not as electronegative, at least not usually. No resonance there. Please understand why there's no resonance there. Okay, let's look at anilines. This is a good time to look back. Anilines, we have the ring. We're going to see the donating, withdrawing groups on the ring. Aniline is a base. Now, some of you may say, well, that lone pair is in a p orbital. Why is it basic? This is sort of the one exception. Usually I say lone pairs in p orbital is not basic. But resonance into the ring is not good because the carbons just don't withdraw that much. It's slightly basic, pKa of 4.6. But hold on, we talked about it being a base. Why are we giving a pKa? That's because organic chemists don't use pKbs. So this is organic 1. If you want a pKb, just subtract this from 14. The pKa actually refers to what? The conjugate acid. Because of that, the lower the pKa, more acidic that is, less basic that is. You got to get that straight. A little bit of review there. Okay? What's the pKa of this guy? Anybody remember? Approximately 10. That means the conjugate acid is less acidic, thus the base is more basic. See, this is more basic. Why is it more basic than that? And we'll end here. Because here the lone pair is delocalized into the ring. Here the lone pair is doing some resonance. Here it's not. Here the lone pair is isolated right there, ready to find a proton. Where's the proton? Okay? Please look at these numbers and getting this straight, and then we'll continue and finish this up. But you got to get your numbers right, pKa versus pKb, that type of thing. Question? The phenol is a neutral molecule. This pKa is a positive molecule. Yeah. The amylin itself is basic. You got to get it. You got to compare
Oxidation, and maybe one more.
Think about it.